Okay, let me start. So welcome everyone back to our visit seminars. Today we have Vincent Crawford from Oxford. Thank you for joining us, accepting our invitation, Vincent. The title of the talk is Meaningful Theorems, Nonparametric Analysis of Reference-Dependent Preferences. This is joint work with Lara Blow. We also have two panelists today, Ernst, Fehr, and Alec Brandon. So welcome and all of you joining us today. The format of the talk is the usual. We have 1 hour presentation with guest panelists interrupting, asking questions and giving comments. After 1 hour, we are going to have a Q&A session for 15 minutes. And after that, we are going to stop the broadcast and we'll say goodbyes, but you feel free to stay for a few minutes and chat informally with the speaker and the panelists. Next week, we have Agatha Prenot talking about how competition shapes information in auctions. So that will come next week. And that's it from me. Vincent, the floor is yours. You have 1 hour.
Okay, thank you. Thank you very much for the invitation. And thank you all for coming. And thanks to the panelists for joining in this. This is, as you can see, joint work with Lara Blow. And really, morally, it should be also joint work with Ian Crawford. But for various reasons, he dropped off as a co-author of this version of the paper. But anyway, morally speaking, he is a co-author as well. And anyway, what I want to talk about today is really how to do a non-parametric analysis of key models of reference-dependent preferences in the context of consumer theory. And I learned from Suzanne Scotchmer, who was giving a talk at UC Santa Cruz when the Loma Prieta quake ended it, that it's very important to tell people what you did at the beginning in case something happens to interrupt you. And the basic idea of the paper, of course, is to derive non-parametric sufficient and almost necessary conditions for the existence of reference-dependent preferences that rationalize some patterns of consumer demand behavior that do not allow a neoclassical rationalization. And I'll motivate that empirically in a bit. But first, let me note, since it's a theory talk, it's basically building on two famous theory papers, one by Tversky and Kahneman in 1991 QJE, one by Kosegi and Rabin 2006 QJE, which are both structural and parametric, and they're basically implementations of Kahneman-Tversky's prospect theory in deterministic settings that are multidimensional and therefore adaptable to economic problems like consumer theory. Unlike the original Kahneman-Tversky paper, which was one-dimensional, there aren't very many interesting questions in one-dimensional consumer theory. And what Kosegi and Rabin do, unlike Kahneman-Tversky, is they have preferences that respond to both levels of consumption, as in neoclassical consumer theory, and changes in consumption relative to a reference point. And they trade off those two things in a way that we'll see in more detail. So what we do is we show that first, unless the notion of sensitivity in this theory is constant, and I'll tell you precisely what that means in a couple of minutes, and reference points are either precisely modelable or observable, then the hypothesis of reference-dependent preferences has virtually no useful non-parametrically refutable implications. In other words, you can rationalize anything, and therefore you can't really explain anything. And that's the grain of truth in a common belief that people have, that allowing reference dependence destroys the parsimony of the theory. And that's the bad news. But it focuses on a case where we have both constant sensitivity and modelable reference points, and there's good news, and that's what I view as the most interesting part of the paper. namely that the model has refutable implications, which we characterize. And in particular, the characterization allows us to relax a couple of very strong structural assumptions that Kosegi and Rabin maintain, namely that the preferences that determine consumers' demand are additively separable across goods, and that there are certain knife edge restrictions on how marginal rates of substitution vary across the gain loss regimes that the theory defines. And we can relax those completely, basically allowing a more general version of Kosegi and Rabin's theory. And as we'll see, the empirical illustration shows that the relaxation is empirically important. Roughly speaking, fit goes up by a lot, and it goes up sufficiently to enough to justify the increased flexibility of the relaxed model. So Kosegi and Rabin's model makes some assumptions that are not well motivated and not either theoretically or empirically, that can be relaxed, and it yields a sort of better version of the model, which we hope will be more useful in taking to applications. So when we judge the whether the fit is sufficiently better to justify the increased flexibility, we use ideas that are building on a notion of Zelton's, which basically say, how likely would it be that random data would fit your model? And how well does the actual data fit your model? And a good model, of course, is one that fits the actual data and that's unlikely to fit random data. And we sort of use a particular way of implementing that idea, which is like some recent work by Fudenberg, Gao, and Lang, but also most like Beatty and Ian Crawford's 2011 AER paper. And the two key findings are, when we relax Kosegi and Rabin's functional structure assumptions, we greatly increase the predictive success of the model, judging by this notion of predictive success from Zelton. And when we look at the drivers one by one in our illustrative example, we find that for a lot of them, the relaxed reference-dependent model does sufficiently better than the comparably relaxed neoclassical model to justify going to the reference-dependent model. So that's the executive summary of what we're doing. What I'm going to do next is go fairly quickly through the empirical history of this kind of model, and then go into the theory and go into the theory in more detail as appropriate for today's talk. So the empirical history started with a famous paper by Kammerer, Babcock, Lowenstein, and Thaler in 1997 QJE, where they had a data set on the daily labor supply of New York City cab drivers. And they found that cab drivers did something that's very far from what's suggested by the neoclassical model of labor supply, which is basically a neoclassical consumer theory model where you're trading off income earned and leisure. And in that kind of a model, when the wage goes up, which is in Kammerer et al.'s analysis is treated as analogous to expected earnings per hour. When the wage goes up, you work more, unless there are very large income effects. But what they found in the data was that the cab drivers, when the wage went up, worked less. And the elasticity of labor supply was something like -1/2, which is a huge difference from the standard neoclassical results for the elasticity of labor supply. And they tried to explain that, and they did explain that by using an idea from Kahneman and Tversky's prospect theory, namely that people are doing something called income targeting. Whether people target is an empirical question, and how they target, the mental accounting that underlies what they do, is also an empirical question. And empirically, it looks like the drivers were doing something like daily earnings targeting. And if you're doing something like daily earnings targeting and you have a good day in the morning, you hit the earnings target earlier and you quit earlier rather than later. By contrast, if you have a bad day, you have to work until midnight to meet the earnings target. So potentially there's an explanation there of the fact that they found in the data that the elasticity on average was something like -1/2, where it was supposed to be positive. So so this has been a controversial model in the empirical labor supply literature. And there are some people, most notably Hank Farber, who've spent a lot of effort basically trying to show that the neoclassical model works anyway, and that there are problems with the reference-dependent model. The paper and the slides are available on my website along with the paper. We'll go into more detail on that, but I'm not going to spend our time today going into more detail on that. But the basic idea, and here I'm gonna blast through the slides on Farber and talk a little bit about Kosegi and Rabin's 2006 paper, which is the key theoretical anchor for the current analysis. And what they do is basically assume rationality in a larger domain of preferences. And the larger domain includes the neoclassical preferences over levels of earnings and leisure, and also a response to changes in earnings and leisure, which are measured necessarily relative to reference points or targets. Reference points and targets are synonymous in my description. And the idea is that if people are irrational, if you focus on levels alone, as in the neoclassical model, if they violate the generalized axiom of real preference, they might nonetheless be rational in the larger space of preferences over levels and changes. And obviously, with regard to parsimony, expanding the domain of preferences is a slippery slope. But here, the idea of reference dependence gives you one chance to expand it, mainly by adding changes to the list of levels, and tells you that it might be useful to do that, but it doesn't suggest any other thing that you could expand. So there's a sort of natural limit to the slipperiness of the slope. And in addition to that, Kosegi and Rabin have a number of assumptions which we're going to maintain too, and which are maintained in subsequent analyses. In particular, if preferences over levels and changes are described by a utility function, that has completely additively separable components of conventional consumption utility and what they call gain-loss utility. They allow reference dependence for all goods, so they don't just have earnings targeting, they also have hours targeting or leisure targeting, if you will. And importantly, unlike Kahneman and Tversky, they close their model by setting reference points equal to their rational expectations in a way that I don't have time to go into adequate detail here. But the basic idea is just before you make a decision, your decision actually influences your future preferences. And you have to predict changes relative to what you expect to happen. And therefore, you can close the model by having a rational expectations notions, which is like a Nash equilibrium in the game with yourself, making the decision now and evaluating the consequences after you make the decision. So it's important that they have a way of closing their model. JJ Meng and JJ's not here today because she's got a conflict, even though it's midnight in China. Anyway, we implement this by using natural sample proxies for rational expectations reference points. And we find that the model, Kosegi and Rabin's model, works pretty well by the conventional labor economics standards. We make a number of assumptions following Kosegi and Rabin. namely that utility is additively separable across consumption and gain loss utility. And we're going to maintain that today. Without that, you basically can't do anything. We assume that preferences have constant sensitivity in the following sense. The reference point divides consumption space into gain loss regimes. In the two-good case, there are 4 of them: gain in income, gain in leisure, gain in income, loss in leisure, and so on and so forth. And with constant sensitivity, preferences over consumption bundles have to be the same throughout a given gain loss regime, but they can vary freely across regimes. And finally, utility is continuous when gain loss utility is determined by the good differences between realized and reference consumption utilities. Question. Somebody said something.
Well, I just wanted
Ernst.
to point out for the audience the enormous significance of this data set that you are analyzing, because usually the workers are not able to choose their labor time,
Yes.
themselves.
Exactly.
So usually the labor markets are not structured that way, but for cab drivers that's the case, and that makes this data set so special. I would also like to add that there is another data set that I collected with in a randomized controlled trial where we have bike messengers.
Yes.
Who choose their labor supply, their daily labor supply, and the number of shifts during the week freely, basically. And there we also document a negatively sloped labor supply curve on a given day. So when they are on a high wage, we exogenously vary the wage. When they are on a high wage, they just earn less. They earn less hard, and it's exactly this negatively sloped labor supply that also Kammerer et al. Find. So this is not a curious finding.
Yeah.
There are other data sets in the literature that support similar findings. I think it's important that the people don't think this is just an aberration, an empirical aberration.
Yeah, so Ernst is referring to a paper with Lorenz Goethe, and I have to say, after you work on this stuff for a while, you begin to think of cab drivers as natural, but they're weird. And indeed, I was in a New York taxi cab with Kammerer, Lowenstein, and Thaler. Babcock wasn't there for some reason when they got the idea. And I thought they were completely insane, just because who cares about cab drivers? But Ernst is exactly right. Cab drivers are much more like neoclassical labor supply theory than most of us are. Most workers in modern economies have hours that are set by their employers, and therefore they don't face the choice that we focus on in labor supply theory. So they're a better way of testing labor supply theory. And of course, you could learn from such tests things that are useful in predicting the labor supply of people who don't get to choose their own hours. So anyway, let me move on though. That's a very good point.
I do just want to quickly point out, I mean, let's not undersell the significance of flexible hour work arrangements. I think in the US, it's something like 20% of the workforce has flexible hours. You know, this is definitely a special sample relative to the workforce in general, but it's maybe like a fifth of the US workforce.
Okay, that's good. That's good. I didn't guess that it was quite that high, but it's not nothing. But we're so used to thinking of more professionalized labor markets. Anyway, let me move on. So final picture from JJ's and my paper. You can see the basic idea in our figure 1. And roughly speaking, figure 1 shows 2 alternative days, a good day and a bad day. And drivers whose indifference maps have kinks at possibly income targets and possibly hours targets. And the story behind figure 1 is if you have a good day, typically in our estimates, drivers stop at the second target that they reach on a given day. If you have a good day, you hit the earnings target first and then the hours target. You stop at the hours target, and therefore your labor supply elasticity is 0. And if you have a bad day, you hit the hours target first and stop at the income target, and therefore your labor supply elasticity is -1. And so on average in the sample, it's going to be something like -1/2. Now, this is a bit oversimplified because in Kosegi and Rabin's model, you also have consumption utility, and my statement is pretending that there's only gain-loss utility. But that's why the model has the power to create a coherent explanation of something that looks completely insane from the neoclassical point of view. So let me move ahead. Quick response, though, to puzzles that you might have about what we're doing. One, people, well, I've said most of this stuff. Let me move ahead. And I mentioned earlier the knife edge restrictions on margin rates of substitution that come from Kosegi and Rabin's constant sensitivity model. And you can see them in JJ's and my table 1. In particular, in income gain and hours gain domain, you have to have exactly the neoclassical marginal rate of substitution between earnings and hours. And it has to be exactly the same in the income loss and hours loss. And comparing hours loss income gain and income loss hours gain, they have to be proportional as a function of the estimated parameters of the model. So these things are assumptions that come from Kosegi and Rabin's simplifying assumption, and which are not theoretically justified, and they're certainly not empirically justified. And one of the things we do is we relax them along with Kosegi and Rabin's assumption of additively separable preferences across goods. So anyway, non-parametric model, I'm going to go quickly, but let me just tell you quickly, consumption vector is Q, and reference point vector is R. Unlike Kosegi and Rabin, we have deterministic reference points, which are conformable to consumption bundles. So in particular, an income target and an earnings target would just be different components of R, and they would correspond directly to quantities of income and quantities of leisure. And we want to look for preferences that are functions of Q and R that are normally going to be increasing in Q and decreasing in R, which is the same as assuming that we're looking for a function of levels of consumption and also changes in consumption relative to the reference point. So with the monotonicity assumptions, they're equally flexible. It's just a little bit neater to think of them as a function of Q and R. In any case, this nests all the earlier cases that have been studied in the literature. Kahneman and Tversky initially just started with only gain-loss utility and only one-dimensional targeting. Farber and Kemmerer et al. Have earnings targeting but no hours targeting, and two-dimensional utility. Kosegi and Rabin have both, and Crawford and Meng have both. So that's the model. This stuff, notation, you probably are, I can explain it more efficiently if I just explain it in the results when we get to them and if we need them. Constant sensitivity is depicted in figure 1 in the paper, which is what I said before, namely that you have a map, an indifference map for each gain-loss regime, which are knitted together in the different panels of figure 1 for different values of the reference point. And one thing that it took us a long time to decide on, which is very helpful, is to realize that each gain-loss regime's indifference map exists all the time and completely fills consumption space. So they're all there all the time. What happens is when you specify a reference point, it divides the space into gain-loss regimes and switches on the relevant map for each gain-loss regime. The second thing that you need to know to understand our analysis is that even though the maps are constant within a gain-loss regime, utility varies with where you are in the gain-loss regime, basically because it's monotonic in the reference point. So while the maps are the same, the utility levels vary, and we have to take that into account in our analysis because we also need that to figure out whether it would be beneficial to you to move into a different gain loss regime that's affordable in your budget set, thereby changing your preferences. So I'll try to make that clearer later on. So neoclassical rationalization, just a very brief review. It's what you think it is. And what we're building on here are three classic papers, one by Afriat, one by Erwin Dewart, one by Hal Varian, which basically do non-parametric analyses of the neoclassical model where preferences are defined only over levels of consumption. And in that case, but not in our case, there is a very strong result that gives you a combinatoric condition called the generalized axiom of reveal preference that shows that you can rationalize neoclassically if and only if the generalized axiom of reveal preference is satisfied. What is the generalized axiom of reveal preference? It's probably almost what you think it is. Suppose you had two different budget sets, and in each of those budget sets, you could afford what you bought in the other one. Then, in effect, each choice reveals a preference for the other one, and vice versa. And that can't be with rationality, because you've sort of shown that when you could afford good B in budget set A, you preferred to choose good A. Good bundle A. And when you could afford good A in budget set B, you chose bundle B. So that's a contradiction. And what the generalized axiom says is that if there are no such contradictions, or if there are no such chains of contradictions, then you can always rationalize. So that gives you a very simple characterization, which is also displayed in Afriat's theorem, which shows that several things are equivalent. A and D are different forms of there exists a utility function that rationalize with different restrictions on them. C is the GARP condition, and B is a set of inequalities which are a way of implementing the GARP condition. So the key things that I want to note here is that there isn't going to be a GARP condition that does it for us in the expanded domain of preferences. But we are going to make use of systems of inequalities very much like B to characterize the implications of rationalizability when we do the analysis in the case of constant sensitivity. So way of thinking about how you construct an Afriat style rationalization is to look at figure 2 down the bottom here. And there you have three different budget sets and three different choices, Q1, Q2, and Q3. I don't know how well you can see the notation figures at the scale. But basically, those three things satisfy GARP. In none of those choices is something revealed preferred to something else that's then revealed preferred to it. And the Afriat rationalization in this case happens to take a particularly simple form, which is depicted in the right-hand panel. And we're going to do something like that later on. Unfortunately, that's, I think, all the intuition I can give for it now. But basically, the Afriat construction is a way of constructing preferences using basically linear programming notions that rationalize the choices that don't violate GARP. So one thing to note that's also important in our later analysis is this figure from Varian 82. You can see a characterization of all of the possible indifference curves that could go through a particular point. So there's a better than set in there called RP of X and a worse than set called RW. And he gives a linear programming characterization of everything that could rationalize that particular choice. And the important thing is that unlike the Afriat preferences in the previous slide, right-hand panel, which are uniquely well determined by the choices, there is a range of possible preferences. And that creates a problem for us because that's why we can't give necessary and sufficient conditions, as I'll explain later. So moving along, what's a reference-dependent rationalization look like? Well, before I define it, let me just say, you might think, so we're expanding the domain of preferences to the point where you can sometimes rationalize things by allowing people to have preferences for changes and levels. Why isn't the analysis just an application of the neoclassical analysis? There are two things that are wrong, that are different in this model that mean that you can't just translate the neoclassical analysis. The key thing that's different,
Vincent,
is
half an hour.
okay, thank you. When you buy a levels of consumption, you're also buying changes. They're algebraically bundled with levels, and you get them at no extra cost. And the second thing is that in your budget set, it might be possible, in effect, to change your preferences by buying a bundle in a different gain-loss regime. So there are two things that make this fundamentally different from the basic neoclassical analysis, and which we deal with in the case of constant sensitivity. So moving ahead, key results on when you can rationalize or not depend on two things, as I said before: whether or not you can model reference points, and whether or not sensitivity is constant. Unless you have both of them, you can rationalize almost anything, as I'll show you in a moment. If you have both of them, both constant sensitivity and modelable reference points, then you can characterize preferences that rationalize choice, as I will also say. And it's that last characterization that's going to allow us to take the model to the data. So first, the negative results. One, with non-modelable reference points, you can rationalize anything. And in brief, the way you do it is you hypothesize reference points for each observation that coincide with that observation's consumption bundle. And then you construct almost Leontief indifference curves, which have kinks at that point. And you do that by making the gain parts of preferences very steep in one way, and the loss parts very steep in another way. And without regard to whether or not GARP is satisfied, you can therefore rationalize anything. So the point of that is, if you don't have modelable reference points and you allow yourself the flexibility of a non-parametric analysis, then the model is empirically empty because you can explain anything. So to put it slightly more polemically, going back to the structural labor econ literature of Kammerer et al. And Farber and so on and so forth, they treat reference points as latent variables. They put some constraints on them, but basically they estimate the reference points rather than modeling them precisely, as we assume you need to do. And so their results might therefore be as much about the constraints they put on reference points when estimating them as they are about reference dependence and loss aversion, which is what the models are supposed to be about. So that's the first negative result. Second negative result's more subtle.
I have a question here in this context.
Say again?
I have a question here.
Okay.
So, because, I mean, what's the difference between modeling and estimating? I mean, because in the end, we don't ex ante know what the reference points are.
Yes.
We only can make some assumptions what they could be. And typically, there is a lot of possibilities here. There is a plethora of reference points in social situations.
So operationally in the theory, the distinction is when you can model them, that means you can precisely predict them outside the model. It's as if you could observe them. So it's hard to imagine that being literally the case. But if you look back at Crawford and Meng and Kosegi and Rabin, in effect, they're assuming that you can precisely model them. By contrast, if you estimate them without constraints, you can make them to be anything that the theory wants them to be or that the data want them to be. And that's the distinction that's being made here.
So basically, you are saying we need to make we need to make assumptions on reference points, derive the predictions, and then test the predictions of the model.
Yes, yes.
And
so, I mean, and in the empirical literature, the way we implement the rational expectations model is basically we say, you wake up, it's Tuesday, it's raining. You expect to happen what's happened on every other rainy Tuesday in your experience. So that's empirically what rational expectations look like. And we fudge one thing, which is that the theory is about precise prediction. And of course, in reality, you're always going to have noisy expectations. We can't find any useful results about noisy expectations, but we think that the theory assuming precise expectations clarifies a lot of things anyway. Let me add one thing. In Farber's early work on this, where he was basically deciding that the reference-dependent model didn't work very well, he assumed that weekdays were the same as weekends, which is not true. But if you then estimate under that assumption earnings targets, the likelihood function basically says, okay, you want them to be the same, your variance is infinite. And that's exactly the problem that he had with his model. So we can talk about this more later, but that's the basic point of view that we're taking.
Okay.
So with modelable reference points, let's assume for the sake of argument that you can model them precisely, but you have variable sensitivity. And to behavioral folk, variable sensitivity is usually described as diminishing sensitivity. But our results don't depend on whether it's diminishing or increasing. They just depend on whether it's not constant. If you have variable sensitivity, again, you can rationalize almost anything. It might be that in your data set with your modelable reference points, you have a bunch of observations that have exactly the same reference point. Then those observations must satisfy GARP. But other than that, the model has no restrictions. So if you don't have anything that has any subset of the data that has exactly the same reference points, then you can literally rationalize anything. So the punchline of these two negative results is that if you're not willing to assume constant sensitivity and modelable reference points, meaning precisely modelable reference points, then the model is non-parametrically empty.
So when
and therefore,
so
characterize what happens when you have those two assumptions on the structure of preferences and how you derive restrictions that allow you to estimate the model. Ernst again.
Just a clarifying question. Do you mean by constant sensitivity, let's say, that my value function, let's say a typical Kahneman-Tversky gain-loss value function, that they are linear?
Then it would be piecewise. It would be piecewise linear in their one-dimensional case.
Okay. Thanks.
It's more interesting though in the multidimensional case. The key thing is that it looks like this. So the maps are constant within each gain-loss regime. So the data come to you. You sort the data into 4 bins: gain, 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 loss, loss, gain, loss, loss. And each bin, in effect, can be analyzed separately and has to be fitted with the same indifference map. And there are also complications that I'll get to about how what more you need to rationalize. But one thing you need to rationalize is you need GARP to be satisfied within each bin. And you also, and you need to have some restrictions on how the bins relate to one another.
Okay.
Okay, so good question. So how do you characterize reference-dependent preferences that satisfy both constant sensitivity and continuity? And I'm gonna, that the key result here is proposition 3. It's got a lot of horrible algebra in it. Let me tell you how to understand it without understanding the algebra. First, look at equation 6. And so there are a bunch of assumptions. Basically, the assumptions are saying it's got to be a two-dimensional or more dimensional model, and the preferences must have substantially different marginal rates of substitution across different gain-loss regimes. So in other words, you could have reference-dependent preferences that actually weren't reference-dependent, so the maps were the same in all the regimes. And then obviously you don't have any particular restrictions on the preferences. But let's assume that the marginal rates of substitution actually differ across regimes, as they would with loss aversion, for instance. Then you get a characterization like equation 6 down at the bottom of this slide. And that says that your preferences are additively separable sum of consumption utility U of Q plus a bunch of stuff on the right-hand side, which is gain-loss utility. And the key thing to think about here is the indicator functions capital G basically turn on the right parts of the maps in the picture I showed you before. And therefore, the key message here is that first, gain-loss utility must be additively separable across goods. That's why you're getting the sums over K. And it must be determined, therefore, by utility functions that depend only on whether you're the gain regime or in the loss regime for good K, like VK plus of Q of K. And finally, and most surprisingly to me, the effect of the reference points must mirror or opposite the effect of consumption utility in the gain part. So in other words, the gain thing, the VK plus of QK must be exactly the same function that the loss thing is of RK. And to put this point another way, if you're familiar with Kosegi and Rabin, what they do is that they make up functional forms that have a functional form like the gain-loss stuff in equation 6 for gain-loss utility, but they also impose the same functional structure assumptions on consumption utility. The latter thing, the first thing they had to do to ensure continuity across gain-loss regimes. And what proposition 3 shows is that unless you have that particular structure of gain-loss utility, you don't have continuity across gain-loss regimes. And I'll tell you why in a moment. But the second thing they did was they extended that to the same functional structure assumptions on consumption utility. They didn't need to do that. And it's important not to do that because that's what allows you to relax additive separability across goods and the marginal rate substitution conditions. So in this equation 6, consumption behavior is determined by the Q parts, and the R parts are exogenous. So the R parts, however, do influence choice in the sense that the things we call loss costs in the paper determine whether it's worth your while to change your consumption bundle in a way that changes your preferences. So I'll tell you more about that in a moment. But let me say one more thing about why this is true. There are a couple of thought experiments that basically determine the proof of proposition 3. The first one is if you look at crossing the border between two gain-loss regimes, say in the direction of good 1, continuity requires that utility doesn't jump when you cross. And unless you had additive separability across goods of gain loss utility, crossing and changing another goods consumption level would cause such a jump. The second thing is, unless you have exactly the same VK of plus function or VK minus function determining gain loss utilities responses to Q, K, and RK, then moving along the line dividing regime 1 and regime 2 also causes a violation of continuity. So that's what the proof shows, and I fear I don't have enough time to say that in more detail, but let's then move on. So the proof is in the slides, but basically the important thing about the proof is that it allows you to unbundle Kosygin and Rabin's functional structure assumptions from additive separability and certain restrictions on margin risk of substitutions. You can relax them. And those relaxations, as I said at the beginning, are empirically very important. And finally, 6 here could be used as part of a structural econometric analysis, but we're going to use it in the spirit of the paper as part of a non-parametric econometric analysis. So anyway, let me move ahead. What does it mean, given that functional structure that we've just derived, to rationalize something with modelable reference points and constant sensitivity? The first thing it means is that if you're looking at a budget set and looking at alternative consumption bundles in the same gain loss regime as the chosen bundle, they must not be better, just as in the standard Afriat neoclassical analysis. And the second thing it means is that if you've got something in your budget set that's in a different gain loss regime, that also must not be better. And what we need to do is to sort of formalize those two things to find the conditions that a rationalization must satisfy and take them to the data. And we do this in 2 steps, which are necessary because of the ambiguity in the indifference curves that can go through a particular point that Varian discovered. So remember the picture I showed you from Varian's paper and the sharp picture I showed you of the Afriat rationalization in the neoclassical case. The Afriat rationalization, which we'll have an analog of here, always works, but it's not the only thing that works. So we need to characterize these conditions in 2 steps. The first step is embodied in proposition 4, and it basically says, okay, suppose you pick some rationalization that works for within regime choices. What do you need to know about the cross regime choices to make the rationalization work? And what you need to know is represented here, and I fear I don't have time to go into detail, but let me just tell you what to look for if you're curious, you can look at it. You can look at it later. The first thing is equation. Okay, so the proposition basically says you can rationalize, mainly condition A, if and only if a bunch of things are satisfied. The first thing is equation 10 or inequality 10, which basically translates Afriat-like conditions, the inequality conditions that I mentioned before in Afriat's theorem for the neoclassical case, into our language. So the notation's quite different, but the meaning of these things is that if you can satisfy all of these inequalities, you can't gain by moving to another consumption bundle in your budget set in the same gain loss regime. 11, by contrast, answers the same question for defections out of your gain loss regime. So you might be able to afford things that are not in the same gain loss regime. And that's harder to check the conditions for because those things have different preferences, even with constant sensitivity. And it's even harder than that because you have to check, unlike in the within regime comparisons, you actually have to check for all possible defections outside of your gain loss regime. And Proposition 4 shows that you can do that using the characterization in Proposition 3 with enough algebra. You can take the characterization in Proposition 3 and use it to give an exact condition 11 for no defections outside of your regime. So, and that's what inequality 12 shows you. So I don't have time to give you more intuition about that, but if you're interested, that should be a recipe for working through it. Now, Proposition 4 is necessary and sufficient.
But 10 minutes.
Okay, thank you. It's necessary and sufficient, but it's not directly implementable because it rests on hypothetical choice of a particular way of rationalizing. Proposition 5 does the same thing in a directly implementable way by using the Afriot style representations, by making a particular thing. And let me just, before I move on, show you figure 3, which shows you how you can rationalize things that violate GARP in a simple case, simply by allowing for reference dependence. So in panel A here, we've got a couple of observations, different budget sets, and they violate GARP in the sense that when you buy Q1, you could afford Q2. And when you buy Q2, you could afford Q1. That can happen. That's a violation of GARP. Therefore, there's no neoclassical rationalization possible. However, the pictures give you rather simple preferences that differ across gain and loss regimes that allow you a complete rationalization quite easily. And they're not unique. The right-hand panel shows that there are a lot of other things that could also do it, just as in variance thing. So there are some more examples of what happens, what goes wrong when you can't rationalize. And one thing you might, I don't have time to talk about, but I'd like to call your attention to is in the left-hand rationalization in figure 3, you might think that the ability to rationalize is determined by whether the preferences satisfy loss aversion. And that's partly true, but not completely true. And I show you why it's not completely true in the appendix to the paper. So anyway, Proposition 5 basically does the same thing in an implementable way. And it gives you sufficient conditions for rationalization that are not necessary because the Afriot preferences are only one of many possible ways to rationalize. So let me move ahead and show you what you get from all of this. And here we chose to use Farber's original data set, which is also what was analyzed in Crawford and Meng's 2011 paper. There is a newer and better data set in Farber's 2015 QGA paper, but we wanted to do an illustration, and we have computational problems, as Farber does, so we didn't want more data, at least not for the purpose of illustration. And the illustration gives you an idea of what's empirically important in rationalizing this data set. Unlike in the labor supply literature, which Farber and Crawford and Meng followed, and Kammerer et al. Followed, we analyze the data driver by driver. So because there is a lot of heterogeneity, and in an exploratory analysis like this, it's quite interesting to see what's going on at the individual driver level. And we do one other thing, namely what's described in the second bullet point on this slide. We basically take the hourly wage variable, which Farber and Crawford and Meng lumped together as the sum of time spent driving plus time spent waiting. and we separate them, and we treat waiting time as a sort of exogenous, randomly varying thing. And that's important in the nonparametric analysis, because if we didn't do that, we'd basically have all of the budget sets pivoting around one end, and therefore GARP would always be satisfied, and the nonparametric analysis would basically just replicate the data without explaining it. We also think economically it's more justified to treat waiting time as an exogenously varying thing rather than lumping it together with driving time. But that's something you could argue about. So I don't have time to go into detail, but Proposition 5 basically gives you a way of non-parametrically estimating from a data set what the preferences look like for each driver. And what you're doing is basically solving a whole bunch of linear inequalities, more or less as Afriat did, but also imposing some constraints that are implied by the Proposition 3's characterization, namely that the gain component of utility has to be the same across gain loss regimes, even though other goods may be in different regimes. And then also implementing the cross-regime defection conditions in Proposition 5. So it's a lot of computational work, but it can be done for most of our drivers. And we also included 6 drivers that Farber and Crawford and Meng excluded with small sample sizes. So here's the recipe. Let me just go on because we don't have enough time. And the first thing, let me remind you what the Zelton measure of predictive success means. It's intended to mean a model is good if it fits the data, and it has a low chance of fitting random data. And the original Zelton measure is sort of an all or nothing thing. You either pass or fail. We found it useful because literal passing is so rare, it's not discriminating, to actually measure distances from passing. And so we use a version of this that DNA and Crawford proposed in their 2011 AER paper called the proximity-based variant of Zelton's measure. And that's the basic ideas. And let me jump ahead and get to the results. First, how does additive separability across goods go? A couple of pictures here. First, for neoclassical models, and remember, these are CDFs of how the pass rates vary and how the Zelton measures vary. And because they're CDFs, low is better. So if you lower the curve, it means less bad stuff happens to the left of the point that you're evaluating the curve on. And you can see that the pass rates are obviously higher with relaxing additive separability for the neoclassical models, as they have to be. But more importantly, the Zelton measures are better for the neoclassical models if you relax additive separability. That means additive separability is not justified for neoclassical models. Same thing for reference-dependent models. Again, additive separability across goods is basically dead on arrival. And the key thing is to look at figure 9, the bottom figure on this slide, and you can see that over a whole bunch of different variations, the reference-dependent model always wants you to relax additive separability across goods, even though that's flexible. Yes.
I have a question here. When you talk about reference-dependent models, I understand what you mean, because you assumed very different reference points, so to speak. You had 18 different reference points, and for each of these reference points, you look how the model does. But when you talk about neoclassical models, what is the range of models that you consider?
There's only one model. There's only one neoclassical model.
Okay, that's clear. Yeah. It's only one model.
So this will become slightly clearer in the next slides. So basically what we're going to do is throw away models that impose additive separability and now focus on models that relax additive separability. And looking at the reference point models, you can basically sort of judge the proximities for different kinds of reference dependence in these figures. And the important one is the one about Zelton measures. And you can see from this figure that the best model is usually the red one, which means expectations-based, conditional on day or night. In our later comparisons, we use the black one, which is just unconditional expectations, which is almost as good just for simplicity. So we do a little bit of conditioning as in the labor supply literature just to sort of see what's going on here. And here we compare models with hours and earnings targeting, and hours targeting. And here there's a kind of surprise. These are the proximities. These are the Zelton measures. In the Zelton measures, you can see that the hours targeting model does a lot better than the earnings targeting model. So the tradition in the labor literature was to focus on earnings targeting and ignore hours targeting. Crawford and Meng did both. But actually, if you had to pick one, you'd pick hours targeting rather than earnings targeting. And I want to stress that in this model, hours targeting is distinguished from the neoclassical effect of leisure or hours because it's about surprises relative to the reference point. So they are identified. And if you had to choose, you'd pick hours targeting. Final thing, let's look at proximities in the aggregate for neoclassical and reference-dependent models, comparing them. And you can see in figure 11, the bottom figure, that it's not clear-cut in the aggregate between neoclassical and reference-dependent models. Reference-dependent models probably do a little bit better on average, but they don't always do better. And therefore, we want to look at individual drivers. And let's focus on figure 13 here, since I'm assuming I have only 1 or 2 minutes left, right? Okay, looking at figure 13, you can see each driver as a spoke on the wheel. And you can see that, roughly speaking, we compute bounds on the reference-dependent models. And we compare them with the neoclassical model, which is the solid black thing. And being out near the periphery is better. So you can see the characteristic pattern here. Let me summarize it. Looking at the middle paragraph on this slide, you can see that the expectations-based reference-dependent model has the same bounded Zelton measure as the neoclassical model for 7 drivers, higher for 6 and lower for 8. But there is something about our computational issues that help you in thinking about that. In particular, the ones with small sample size all have exact neoclassical fits and therefore exact reference-dependent fits. But because the neoclassical model is less flexible, it wins the Zelton comparison. And that's good news for the neoclassical model, but it could just be overfitting. For 7 others, the sample sizes were too large for us to even estimate. And therefore, again, the neoclassical model wins because it has less flexibility, but that doesn't really mean anything. For the 8 drivers in the middle, where we can estimate and where the sample size is large enough so that things don't fit exactly, the expectations-based model with reference-dependent has a higher Zelton measure for 5 of the drivers and a higher measure for the neoclassical model for 3 drivers. So roughly speaking, there's a lot of heterogeneity in the data. And for roughly half the drivers, when you can tell the difference in the data, the reference-dependent model does better. So empirically, probably you would want to allow for reference dependence, possibly in a latent class model. So I'm used up my time. Let me stop now. But I again express a willingness to hang around as long as you guys want to talk after well, beyond the 15 minutes, but to talk after. Yep. Thank you.
Thank you very much, Vincent. This is great. So let's move to the. We went over time, but we still have 10 minutes for the Q&A sessions. So as is typical, we will start with our panelists. If you have any sort of remaining comments or questions, please go ahead. Alec, you muted yourself.
Yeah, so one, this is maybe more a comment than a question, but Vince, you're sort of making like claims like it does a lot better under this approach versus alternatives, and it'd be nice to see some confidence intervals to get a sense of how noisy these things are. I don't know based on the computational issues you were describing, I don't know that bootstrapping is going to be the solution that that's the solution that first comes to mind for me. I don't know how practical that's going to be for you. But yeah, that's just sort of one comment / suggestion for something you were just mentioning. Something that it's a little bit more of a question though is, you sort of made this point about modeling reference points and then also the sensitivity assumption that if you didn't take a stance on those and you just sort of left them as latent, you could rationalize anything. Is that still true if you like fit the model in sample and then try to apply it out of sample or test some prediction of it out of sample?
It's not automatically true. So certainly you could sort of test the effective flexibility as you're suggesting by doing beyond sample fitting. However, the basic result suggests to me that if you did that with conventional functional forms, then basically your results would be as much or more about the functional form assumptions than they are about reference dependence and loss aversion per se. So as I said earlier, we looked for a lot of different results, sort of testing, the importance of the different kind of restrictions in the theory. So the basic question you want to answer is this explanation really reflecting loss aversion? Or is it reflecting some other arbitrary assumptions I made without testing them? And in a sense, the nonparametric analysis is a way of testing them. So that's the way I view the results. I don't know how to do confidence intervals nonparametrically. But anyway, that's something we've looked pretty hard in the literature, and right now we're sort of at our computational limits, just estimating the model. But I can think of simple things to do. For instance, leaving one observation out of the data set and trying that across all the possible leave outs. But the sample sizes here are too small to make that a practical alternative. So thank you.
Ernst, yeah.
Yeah, so there are some, taken literally, some inconvenient implications somehow for empirical research here, which is you have to go through a whole list of alternative assumptions on reference points. And maybe there are even others that you have not yet considered. And then for each you make a prediction, and then you kind of, you have no way to decide which reference point is the better one. So, what I find an inconvenient truth, so to speak, is that you don't provide us with a method. In fact, you say it's not possible to identify the reference points empirically. But if I would go to out of sample prediction exercises, that could be give us a grip on the problem, perhaps. I mean, in particular, when I combine this with experimental, you know, you have lab drivers, but in a more controlled setting of a laboratory experiment, it may be possible perhaps to constrain the choice, the set of situations that you don't just identify with parametric assumptions, but with that when you predict out of sample.
No, certainly there's a nice Abler, Falk, Huffman, and somebody else paper which sort of experimentally manipulates things that are like reference points. So one could do that. One thing we do with, there's a paper I have with JJ and some Chinese colleagues where we elicit reference points from Shanghai cab drivers. That's now up on my website. And that basically justifies, or sort of, it shows that what Crawford and Meng did works approximately in the same way as elicited reference points do. And elicited reference points make the model work a little bit better than estimated reference points. So there are a number of things you could do, but I think the basic idea of targeting is probably robust to most difficulties in estimating reference points.
Yeah, thanks.
Are there any other questions in the room? Okay.
Okay. Thank you all very much.
Yeah. So why don't we stop the broadcast?